All right, so it's about 6, so let's get started. So welcome to the review. Hopefully people will come later. I heard there's like a conflict with like a camera, but anyways, that's why I'm recording it. So, right, finally we need to just answer questions you guys have, and in particular, the first ones should be from the practice midterm, numbers 4 and 5. Right? So like, I think we probably want to see number 5 first. That has very few parameters and is the Cauchy-Euler equation. Okay. So, let's copy it down first. Number 5, and practice midterm. Okay, so part A is the general solution to this Cauchy-Euler equation. X squared y double prime plus 7xy prime plus 5y equals 0. And then part B is find a particular solution to basically the same equation. So I guess I'll copy it again. Equals 2x plus x squared. Okay, so great. Part B says use variation of parameters, but like, I don't know. I thought it was easier maybe with undetermined coefficients, but we'll do it. Maybe we'll do it both ways. Maybe one way fails. Okay. So, right. Let's start off with part A. So for the Cauchy-Euler, we assume that y has what sort of form? XR. X to the power of r. So then when that's what we assume y is, we have to find its derivative and second derivative to plug in. So what's its first derivative? Rx r minus 1, and then an arrow r minus 1. Yeah. So it just keeps differentiating like you would a polynomial. X. Some underlying assumptions are that like x, we always assume it's positive, so that way we don't ever have like division by 0 if it's a negative r or something. But we shouldn't have to worry about that. Okay, so what we do with this is we plug into the equation, solve for r. Basically the same thing that you do with like the auxiliary equation with the constant cases. So like when we plug it in, so what do we get? Okay, first term is, okay, so the idea behind this substitution is that all of the terms will end up with the same power of x to the r. So like, I'll usually just lump the power into whatever the power is for that derivative. So y double prime has a r minus 1, x to the r minus 2, and then we plus 2 from that x squared in front. We can see that it goes away. Then we have 7 times xy prime, so 7r, x to the r minus 1 plus 1 from that one in front. And then 5y, so 5x to the r, and that equals 0. Right. And then you can see that like, right, the minus and pluses of 1s and 2s, and those exponents cancel out. In the end, we pull out the x to the r, and then see what kind of constants we get with the r's and whatever the equation had. So we have r squared minus r plus 7r plus 5 equals 0. Okay. So are there any questions so far? All algebra. And then what we do now is we want this inside to be 0. Right. So, or sorry, not inside, but we want this bracket to be 0. So for, let's reduce it a little bit. So for r squared, this becomes a plus 6r plus 5 equals 0. How does that quadratic factor? Plus 1 and plus 5, good. So we get 2 roots, -1 and -5. Or you could use the quadratic equation if you don't like factoring. Right? So once we have the roots, then we go back to our original function form, basically kind of like how with the constant case you go back to the e to the rx form, and we have those 2 r's as our 2 independent solutions. So just make sure it's recording everything. So this means that our general solution, or general solution, C1 x to the -1, and then plus C2 x to the -5. Right? Or you could write 1 over x to the 5th. It doesn't matter. Same thing. So that's like the easy part to this problem. Right? Okay, so yeah, one more check. Any questions? Part A? Yeah.
Any difference between this number and y equals to ex?
The derivatives will end up being a little bit different. Right? The derivatives are in this way.
Yeah.
But when we use the exponentials, right? If we use y equals e to the rx, then y prime is r e to the rx. Y double prime is r squared e to the rx. Right? Like for example, if we look at the second derivative, that's not the same coefficient. Right? This is r squared minus r.
Can we use this way to solve this problem?
No, because it's not constant coefficients.
No constant.
Right? It has this function of x in front. Right. So this is only 2 second orders we'll see. Either constant coefficients or ones with these x terms in front. Well, I guess this one has nothing. When you see the x terms, that's when we know it's a Cauchy-Euler equation, and we use this function form. When it's constant coefficients, it's our usual exponential function form. So that's how you'll want to identify the problems on the exam. Okay, so other questions? Yeah?
How can we make sure this is the Euler equation and not the substitution where v equals y over x? Since it's a
Oh, these are second order.
okay.
Yeah, these are second order. Yeah, so made the order. Other questions? Okay, so let's do part B, the hard part. So the exam says use, hints at variation parameters. So let's do it that way definitely for practice, because that seems to be probably strange when you see it at first. So part B, the hints to use variation of parameters. So I hope you guys have the worksheet that I printed out last time. At least you've seen it, or you can see it online, whatever. Yeah, as long as you have the reference. Because it kind of outlines the steps, which hopefully he did in class today. So the first step is always to get the independent functions that generated your general solution. Okay. So first, right, identify the independent solutions. So second order, we should have 2, call them y1 and y2. And we refer to the general solution. So what are the 2 function types from the general solution? Yeah, basically whatever is after the constants. Right, 1 over x or x to the -1. And x to the -5. So that's the first thing you always want to do is identify these guys. Okay? So like the idea is like, in the end, so the whole premise of variation practice is that we assume that yp is of this form, like u1, y1 plus u2, y2, where the whole problem is basically just how do we get our u1s and 2s. So that's why identifying y1 and y2 first is basically essential. From here, once we have identified those, we solve for u1 and u2 by like a system of two equations, right? We have to solve the system for u1 and u2. And actually, the system only tells us what the derivatives are. But that's okay, you can always just integrate that to get the original function. Okay. So, what's the system that we solve? What's like the first equation that we have? Something equals 0. So, right, you have to know the system in order to solve it, right? So here's the system. The idea behind both of them is like they're both equations are involving like the product of u1 and y1 with some derivatives. Okay. The u1s always have a prime. The y1s, or sorry, the u's always have a prime. The y's go from no prime to prime. So like you have u1 prime y1 plus u2 prime y2, and this one's set to 0. The next one, okay, well, I kind of told the way to like memorize it, right? The u's always have the primes. So what should be multiplied to them this time? y1 prime and y2 prime.
And that's the right-hand side of the equation?
Right. This equals to whatever f of x is on the right-hand side. So definitely have to know the system. Okay. So does anyone have the worksheet out in front of them, perhaps? Okay. So what's the big warning about like this f, or setting up variation parameters? I made like a little mark as well.
Make sure that the constant in front of the y double prime is a 1.
Yes.
Or else it doesn't work.
Yeah. So what this means is we have to go back. Okay. So what's our equation in the first place, right? For part B is this guy.
So that's not in standard form because it has an x in the front.
Yeah. Right. So this is our equation. There's this problematic x squared in front. So what we have to do is divide everything, well, in principle, you would divide everything by x squared. You don't need to do it to the whole equation. You're only interested in like the right-hand side, right? So you have to watch out for this, right? Even if it was just like a constant, like 2y prime plus 7y prime plus 5y, that 2 can throw off the calculations. It happened to like another grad student when I was teaching. It's very, very subtle. So, right, that's something to keep in mind. Okay. So let's basically take this with our problem, right? So u1 prime and u2 prime are things we have to solve for, but we have y1 and y2. So we have u1 prime, y1 is just x to the negative 1, plus u2 prime, y2 is x to the negative 5, and we set that equal to 0. Okay. Next equation is where things get interesting. So now we need derivatives of y1 and y2. Okay. So what's the derivative of y1? Negative x to the negative 2. So let's plot the negative in front, u1 prime, x to the negative 2. Okay. What about this derivative of the second one?
Negative 5x to the negative 6.
Yeah. So it's like the same pattern from polynomials, right? Negative 5, u2 prime, x to the negative 6. And then now, the right-hand side. Right. It's almost this, right? Right, is that, but then we noticed that out in front was an x squared, so what should we do to that right-hand side?
Divided by x squared.
Divided by x squared. Right. Like I made that same mistake when I was, preparing this. Right? I didn't divide by the x squared, and I was like, this solution makes 0 sense. It needs to be there, and it works out. So,
2x to the negative 1 plus 1.
yeah. In the end, yeah. So this sort of we can just continuous. This is 2x negative 1 plus 1. Okay. Good. Okay. So now mainly it's like how do you solve for functions, right? It's like you want to solve for u1 and u2 prime, but you do it the same way that you would like of the system that you want to like eliminate one of the functions. So like how you always do this is by adding or subtracting multiples of one equation to the other one. Usually it's easiest, I think, to utilize the first one and then eliminate one of the variables in the second one. So like, what should we do to, so like how should we do it here?
Multiply by x to the negative 1, and then add that or subtract that from the other one.
Yeah, so we notice it's off by a power of x, so we need to scale it by x to the negative 1. And then, well, this one's already negative, so we can just add it.
Oh, right.
So, okay, so this is our system. So then what we're going to do is take second minus or plus x to the negative 1 times the first. So I know that looks kind of weird, but mainly what do we get? So to do that, this would become a u1 prime x negative 2 plus u2 prime x to the negative 6 in the first equation, when it's scaled by x to the negative 1. So when we add it, what terms cancel? The first one, the u1 prime x negative 2. What's left for the u2 prime?
Negative 4.
Negative 4 u2 prime x to the negative 6. And then what's left on the right-hand side? Well, the second equation was left alone. Well, the first one was scaled. So it's just this thing. Right, 2x negative 1 plus 1. Okay? All right, so any questions so far on like these the setup for the variation parameters? And we did like one step solve. Yeah.
So after this example, can you go over the other way he did it with Cramer's rule?
He gave us like 3 determinants, 3 different ways, and then like u1 prime equals that.
Yeah. Well, it kind of depends on the problem. Like this one, the matrix is pretty simple, but like he did it the other way with like Cramer's rule, where you can actually.
I've seen it with like a.
It's essentially the same thing. It's like a linear algebra trick, basically.
So it would be like you'd have like a 2 by 2, and it would be like y1 over y1 prime,
Yeah.
y2 over y2 prime.
Yeah. And then you take like the determinant of that.
Yes.
Yeah.
Divided by, I think.
And then you move those two over, and then you do it again with the right side in the first column, and then the right side in the second column. So you do 3 different determinants.
I have it written down. I could show it to you real quick.
Would that way easier than the A, B, C kind of?
My handwriting's a little
Undetermined coefficient?
messy,
Yeah.
but
Generally, undetermined coefficient is easier than this, but this always works. So that's the trade-off.
Right on.
yeah. So let me. Yeah, my handwriting's a little bad. So this is like the Cramer's rule, where you have y1, y2, y1 prime, y2 prime, and then back here.
Yeah.
This is Cramer's rule, is the determinant. I think, if I remember correctly from the last class, this is like Wronskian or something.
Yeah, that's a Wronskian.
Yeah, that's why he uses W. And then, so W is just this matrix, basically.
Yeah,
it's W1 is the right-hand side plus 0 for the augmented part of the matrix here.
Okay.
And W2 is this part. And then you can solve for U1 by dividing first half, then it's going
Right, yeah. So, I mean, there's the determinants here, right?
Yeah, basically.
Yeah, so this one should be like y1 or this one should be like y2 and y1. Right, yeah. I remember saying that, yeah. He's never noted as pure.
Yeah, he said this is called Cramer's rule.
I think
I want to Google this.
No nomenclature, whatever, right? Yeah, that's why I was like Cramer's rule. They do, yeah, they do the same thing. They do the same thing.
Right, they're both just different ways to solve the
Yes.
system equation.
Yes. I don't know. I kind of think this way is easier.
Yeah, I kind of like this way too, but I can see, well, the reason he did it that way is this one is involving trigonometric functions, and obviously that's a lot harder to do for these. So basically it's like if you can't solve the system of equations, then you use the Cramer's rule.
I see. I think even a trig function is not too bad. Like if this was like sine and cosine here.
They were tangents. Tangents and secants.
Well, tangent takes derivative.
Yeah, it was
Wow,
like,
okay then.
yeah, the right-hand side was tangent vectors.
I see.
Yeah.
Okay. Maybe we can do that later. We can do that after this too. Okay. So anyways, right, if we go this way, it's pretty easy here to solve for u2 prime. Just isolate it. So like u2 prime is -1/4, and then you have to multiply x to the 6th over. So you have 2x to the 5th plus x to the 6th. Okay. That's what we get for u2 prime. Oh, I'm gonna have to split up this bit. Okay. Well.
Yeah, that's what it was showing.
Okay. So then. So then what you can always do now is like use this, plug it back into probably the first equation, easier to work with, and then solve for u1 prime. Okay. So like, right. So then plug u2 prime into the first equation. What do we get? 7. Good. So when we plug that in, okay, u1 prime, x -1 is on its own, and then we have u2 prime, which is this thing. That thing. So -1/4 parentheses. There's an x to the -5th on the right, so what it'll just do is lower all these powers by 5. So we have just 2 plus x equals 0. Okay. And then just rearrange it, multiply everything by x. You can solve for u1 prime pretty easily as well. u1 prime is 1/4. Multiply everything by x, we have 2x plus x squared. Yeah. So that's, I guess, this way of doing the variation of parameters then.
Yeah, the other way was pretty confusing. I'll be honest.
We can try to make the parity after we solve for u1 and u2. I mean, well, once you have u1 and u2 prime, it's very easy. Just integrate them and you get u1 and u2 back, right? So, okay. So, or maybe, oh yeah. So, okay, so integrating, I guess, so this is like step 2, solve the system. So step 3 is to integrate and get u1 and u2. So u1, integrate that thing. Let's just keep the 1/4 sound in front. So if you just plot the constant, so we just integrate this on its own. What's the integral of 2x? X squared. And then integral of x squared. X squared. Yeah. do the same thing for u2. Let's keep the negative 1/4 at the front. Right, so 2x to the 5th. What does that integrate to? Yeah, x is 6. And then it would be divided by 6, but there's a 2 on top, so it's overall divided by 3. And the last term is 7x to the 7th over 7. Great. Once you have this, you're basically set. Because just go back to, what's the whole point? This is how our particular solution looks like. Multiply this thing to the first one, and then this one to the second one. Make sure you do it to the right one, though. This one has to be multiplied to x negative 1. The second one to x negative 5. So, okay, I guess I'll add it here. Okay, so then yp equals u1 y1 plus u2 y2. Plug this in. So y1 was x to the negative 1, so all it'll do is just lower all these back down by 1 power. So we have 1/4 x plus x squared over 3. And then this one's minus, so I guess you have minus 1/4. This one's multiplied by x to the negative 5th. That was our y2. So it lowers all these down 5 powers. We'd get like x over 3 and x squared over 7. Right? And if we add this all up, right, this is 1/4 minus a 12. So that's 1/6 x. We have this one's, okay, this is right.
4 over 21.
This is, right, 4 over 21, yeah. Yeah. So then the next one becomes 1 over 21, right? X squared over 21. So, right, what happened here was this is really x over 4 plus x squared over 12 plus x over 12 plus x squared over 28, right? Oh, sorry.
Minus.
Minus and minus.
Minus.
Thank you. Right. So 1/4 minus the 12th is the 6th, and then this is a kind of a weird difference. Like if we find a common denominator, you can get like 4 over 84. Divide by the 4, that's 1 over 21. Anyways, it's algebra. Kind of tedious. But this is the YP that you want. Okay. Are there any questions? Do you want to see the computation work that I did? Or no? Okay. Question?
So y1 and y2 are just the solutions that we found earlier?
Yeah, from the homogeneous, the complementary case.
Okay.
Yes. Yeah. You can differentiate this, or not differentiate, plug it into this equation. It'll work. Right. It will work. You can kind of see the trick. Like this term actually takes care of the x squared. This term takes care of the 2x. If we differentiate this twice, it goes to 0. If we differentiate it once, it's just 1/6. So right now, there's 5x over 6 plus 7x over 6. That's 12x over 6. That gives us 2x. So it does work. This one, there's a third derivative involved. Like, take a derivative, get scaled by 2. Take another derivative, you just lose the x, but the 2 stays. So like, maybe I should just do it. But like, if you plug it in then, you get 5 over 21 plus 14 over 21 plus another 2 over 21. 5, 14, that's 19 plus 2 is 21 over 21, that's 1. Divided by x squared. Yeah, sure. No, yeah. I figured I should. So let's do it on the bottom.
Yeah, I'm not keeping rid of that. Kind of
Magnetic dipoles. I was a physics major and I did not even like that subject. But that's
Magnetism and electricity is so much worse than every other kind of physics. Let's be real.
Okay, so yp is this. So maybe just to keep it all here, yp prime is 1/6 plus 2x over 21. Yp double prime is then 0 plus mu over 21, right? So now when we plug this into the equation, okay, x squared is multiplied to yp double prime, so 2 over 21. 7x is multiplied to the 1/6 plus 2x over 21. And then we have 5 of the original. X squared over 21. And this is supposed to equal 2x plus x squared. Okay. Really, we're just kind of verifying for now, right? Combine all the terms, right? Or just, I guess, expand these out, right? What is this really? This is 7x over 6 plus 14x squared over 21. So, okay, this is 5 over 6 and 5 over 21. Okay. So what do we do? We group by powers, right? So we have x squared, 2 over 21 plus 14 over 21 plus 5 over 21. And then x times 7/6 plus 5/6. This is x squared 21 over 21 plus x times 12 over 6, which is, x squared plus 2x. You're generally not expected to. It's like mainly if you have time at the end, you want to check that you did it right. I mean, no, in all seriousness, right? You do a problem, say in real life, right? You want to check that it makes sense. If you have time to do your due diligence. Okay, so are there any questions on this? Okay. Step 1 is to identify what y1 and y2 were from the homogeneous case, the 1, 0 on the right side. Your complementary solution. Right, in the end, this is what you're after, right? Solve this system for u1 prime and u2 prime. So for us, it turned into this. Right? So usually we use the first equation to eliminate something in the second one. So we eliminated u1 prime from the second equation. So we can solve for u2 prime. Plugging it back into the first equation allows us to solve for u1 prime. Right? Once you have the derivatives, you can just integrate it to get the actual functions. And then you know that your solution is given in this way. Right? u1 y1 plus u2 y2. Again, this only gets you yp. So if you just find a particular solution, you're okay. If it said find a general solution, what we have to do?
You have to add it to the
Add yp to the homogeneous one, the one that you got in part A. Right? If it said find a general solution, it says particular here, you can just use yp. Right? Okay, one comment is that here, right? We've had plenty of experience with things that we can't integrate, like sine of t squared, I think is in the homework, or like e to the x squared, right? Stuff you can't integrate. If that ever pops up in these u1 prime, and I guess u2 prime, so what you'll notice here is that it doesn't matter if we add a constant to these guys. It doesn't matter. So if you can't integrate something, just use like a definite integral. Make it from 0 to x of whatever was there, I guess, dt. Right? So what I mean to say is like, right, here we could find an antiderivative, but suppose u1 prime was like e to the x squared, well then you would set like if u1 prime equals e to the x squared, something you can't integrate, you would still just use a definite integral. You still do that. and it's perfectly fine. And he'll probably say it's okay to use definite. Why is this okay? Is because if we add a constant to our U1 and U2, here, right? If we add a constant here, all that does is it adds a constant here, right? It'll just add more of Y1 and Y2, but those are complementary pieces, so it does nothing at the end of the day. Did he talk about that a little bit? I hear a no and I hear a nod.
He did say that you can't use the definite interval.
Okay, yeah. The reason is because like what it does is like it predetermines your constant, and that doesn't matter because you're gonna have a general constant from the complementary piece anyways.
I think he said he was going to try to not have definite intervals on the midterm.
Sure.
But yeah, he did say you can do it.
Okay, cool. I feel like this is always like your plan B if you can't do it. Yeah. Okay. Would you guys be interested in seeing the Wronskian way or the Cramer's rule way? Okay, maybe at the end then. Like we can revisit this. Okay. Oh, actually, no, wait. He's gonna post the solutions to these on the weekend, so he'll probably do it that way. So maybe he'll do it that way. Yeah. He'll probably do it on the solution that I'll post on the weekend with the Cramer's rule / Wronskian. Okay, great. So, next question. What problem from the midterm then is like next most important? Yes?
Number one is kind of.
Yeah. The first couple are conceptually easy, computationally hard. Number one. Oh, what? Okay. It's like a light. Okay, so number one is so an explicit solution. Okay. X1 prime plus x plus the third y. Okay. No addition conditions then. So it's just this. All right. So, what kind of equation does it look like at the offhand? Sort of linear. Except you have this, right? What type of equation is that usually? Bernoulli, right? So this one's, I think, kind of he's playing something kind of sneaky here. It's not like if you do this like, I don't know. So if you treat this as Bernoulli, it'll work. But I think it's easier to do something first that he recommends doing with this equation. That's for later. Right, when you have a Bernoulli with this on the right side, what do we usually do to this? Yeah, like you divide by 1 over y squared, so it's multiplied by y squared. Yeah, so multiply by y squared, and then it'll become a little clearer. So we have x y squared y prime plus x plus a third y cubed equals e to the negative 2x. Right? So from the professor's like kind of way to look at the Bernoulli equations, what do we set v equal to? Y cubed. You look at what this one is, and that is what you'll set for v. The other thing is also, you also see this sort of term, y squared y prime. That's like another sign that you should use, v equals y cubed. This is one of the ones in the table. Right? So it's kind of two signs that's the substitution rules. Okay. So, right, v going to equal y cubed. So then what's v prime? 3y squared y prime. And then we plug this in. So, okay, x, whatever. What does that become now? The y squared y prime. V prime over 3 or 1/3 v prime. Same thing. And then x plus a third. What's that term become now? V. Flat out v. And then either like 2x on the right side. Now this is almost a linear equation. So now is where you want to divide by the x, but you also need to multiply by 3, you see. So we actually have to do that simultaneously. Okay, so, and then multiply by 3 over x to get rid of, to get rid of this coefficient. What's left on the inside here? Yeah, 3 plus 1 over x. Yeah. V equals I hope this turns out better.
It's a little gross, but
This is okay, yeah.
now it's
Yeah, the main point is linear. Right? It's like when, well, we saw that it was a Bernoulli, so it's like you know you expect it to become a linear equation that you can do with like an integration factor problem.
P of x is 3 plus 1 over x. So we have to find the integration factor.
Yes, so you want to identify this as your p. This is your p. So then, the integration factor r of x is going to be e to the integral of this guy. So what is that integral?
Yes.
Plus
Minus 1. Natural log of x.
oh, now it becomes ln of x.
The same thing, man. Like you're right. One should integrate and integrate when I use right.
Oh, goodness, man.
So that's the integration factor. And
You can split it up and then the natural would cancel.
right, so you want to split up the sum for sure, right? Especially to get rid of this ln. That's kind of the signal to actually split it up. E to the 3x times e to the ln half of x, which is yeah, x e to the 3x. Do we need to care about keeping the absolute value?
Normally, no, but
Actually, normally yes.
well, usually it depends on the initial conditions and if
Right.
it's positive. But you didn't give the initial conditions, right?
Yeah, he didn't give them, but then usually we would just keep the absolute value there.
Yeah.
For the integration factor though, I'm saying we can actually drop it. Why?
Because you're multiplying 3 over 3 cancel it out.
Sort of, like it's multiplied to both sides. So if it's plus, great. If it's minus, it will cancel the minuses. So you don't need to care about the signs. So that's the integration factor. So then what we do to it is we multiply to both sides. And then of this equation. And what we know is that it turns the left-hand side into a perfect derivative. The right-hand side is whatever the heck is left. Right? So the left-hand side becomes a perfect derivative of what?
Oh, sorry, it's x e to the 3x times b.
Right, it's always your integration factor times what you're solving for. So x e to 3x times b. Right? The right side is whatever's here times this guy. Yeah, so let's write out some steps. So we'd have x e to 3x times 3 over x e to the negative 2x. We see that the x's here canceled out. And the exponents sort of like simplify, right? So what we're left with is indeed x. Oh, let me move it up. Right, so just we copy this left side. Now the right hand side is how we get left with
3 to the x.
yeah 3 to the x. Because 3x minus 2x just leaves us with 1x. So now this looks so much better than what we had initially. What we have to do is, well, integrate, solve for b, and then don't forget to substitute back and solve for y. So, okay. So, what you do now is integrate. The left-hand side is always nice because it just undoes that derivative. So we get, what is that? S either 3x times b. And then the right side, we have to integrate 3 to the x dx. What's that integral?
3 to the x.
Okay, plus c. Integral of e is itself, at least when there's no constant up there, and plus the constant integration. So now we isolate for b. So b equals dividing this out, 1 over x. I was going to write it out all in some steps. So instead of dividing by this, you can always multiply by the negative exponent. Always have that in your arsenal. And multiply to 3 to the x plus c. And then, right, and multiply this through. This one becomes, yes, 3 to the negative 2x. And then c to the negative 3x. Yep.
This stuff from 1 to 4, is that being okay?
Here?
Yeah.
Yeah, that's fine too. Yeah. Just make sure that the brackets around the c, because the c will get multiplied by 1 over that integration factor. Good. So this is v. Well, all we need to do is, what was v originally? Y cubed. V equals y cubed. You know that v is y cubed. So this is really saying y cubed equals all of this. So if we just want y, all we really need to do is just recopy it. And then right, since it was cubed originally, we have to take 1 over. And then that's the explicit solution for y. We found an explicit form. Still a general solution because we don't have the c. Right? We didn't have an initial condition to determine. Okay, good. Is that good for number 1? So, right, maybe just to recap it, right? See this sort of equation. It looks kind of like a Bernoulli. So the professor usually doesn't multiply by that. Well, like, I guess divide by this, or in this case, multiply by y squared. Make the substitution for whatever this non-differentiated term is, and then follow that through. Right? Get your linear equation, solve it with the integration factor, and then don't forget to substitute back for what v is in the first place. Yep.
So if our v instead of y cubed happens to be instead of y squared, and we square root it, that means the general solution will have to be plus and minus.
Yes. Yeah. Good. Good. Yeah. If it happened to be like, even if it was fourth too, it'd still be plus or minus 2. Yeah. Good. Good. Cool. Okay. So next question. Right. Also very much like this one, computationally hard, essentially maybe not. Okay. So just a reminder for everyone else who's come in, like the third quiz is on the 2 chairs up here. So you can come get them before you need to go or after the review. So number 2. No silence.
Oh, that's right. It's very good.
Yes, I hear people talking about the right method. So
Stop.
basically just to solve this equation. You have the y to write that video.
That's what there's also this little slight computation of The only that's intimidating to me is the one that's like, you've got a bucket of salt. That's like so conceptual.
It says an implicit solution is okay. Let's see if we can somehow get an explicit one. Right. First thing is like there's exponentials in y, so you automatically know it's not sitting here. That's definitely something that should tell you, okay, you're probably looking to make some sort of unique substitution or separate. Okay, so what do you guys do first for this problem?
We can subtract y plus 1.
Subtract the y to the other side, right? So what we get is x plus 1 cubed to the negative x dy x equals right negative. Thank you, I brought that. So we have this, and then now, well, what does it look like?
Separable.
Separable. This is all functions of x. This is all functions of y. We can probably move all the y stuff to the left, move all the x stuff to the right. Okay. So what we get, and the right, keep the dy on the left, move the dx to the right. So move it up. So dy is going to be divided by this. So we have, let's that negative side. Let's just keep it on the right side. It doesn't matter. It shouldn't matter. Okay. So, right, we have e to the y plus 1 squared and divided by e to the negative y. You can keep it down here, or you can just move it up here. Okay. Dividing by e to the negative y is same as multiplying by e to the positive y. Okay. Always use that exponential, negative versus ratio. Right side will have x divided by this. So we have e to the x plus 1 cubed, and then the same thing, either divide by e to the negative x or multiply by e to the positive x.
Forget the negative.
Thank you. Yes, I did. Thank you. All right, cool. So now, what do we do to both sides? We want to integrate. How are we going to integrate both sides?
We can solve.
Yeah. So that's really all we have to do. So I haven't heard much from the right side or the back. So I want to kind of ask you guys first then. what's the use of, just to be fair, right? What's the use of that you use for, say, the left side?
U y plus 1.
You're in the front. I don't mean to be mean, but like, just make sure, like, be fair, right? So, you give the answer away, e to the y plus 1. So, left side, e equals e to the y plus 1. What about the right side? For this side? Yeah. Maybe let's just call it something like W, right? So the mainly like, if this is your U and this is your W, what's your DU? E to the Y, and then a dy, right? So same thing here, what's your dW? And then over here the dx. Right? So then when we plug this in, what are we going to get? Okay, the main thing is like, these guys are perfect, right? Especially if you remember to, when you divide by e to the negative x, it's multiplied by e to the positive x, right? That really played a role here. So, what's the left side integral become? What does the entire top become? Du. What does the bottom then become? U squared, yeah. Right hand side then, what does the entire top become? dW. And the negative side as well. And then what do we have at the bottom? WQ. Alright, so now when we integrate this, what is the integral of the first one? Negative 1 times u to the negative 1. And on the right side? So now I feel bad that I didn't ask you guys more. So what about the right side? What does that integrate to? Right. So it's like, and then there's a negative in front too. So it's negative, negative, over 2 w to the negative 2. Right. And then, right, plus c. Thanks. Plus c. And what we want to do last is, don't forget to substitute back what u and w are. Okay? So, what are u and w? Okay. Right, so let me undo the signs here. Let's become pluses. So we have 1 over u, which is negative 1 over e to the y plus 1. 1 over 2 w squared. This equals x plus 1 squared plus c. Okay? E to the y here. All right, so we don't have to find it explicit yet. Maybe we can do that later. I think I see it. So what we need to do is determine this c. Right? And we're going to use our initial condition for that. So, so when we solve for c, we have to just plug in our initial values. So solve for c with the initial conditions. Okay, so we plug in, happens to be both at 0, we plug in 0 for y and 0 for x. So what does the left-hand side become? Negative 1/2. And we saw that negative sign. And then what does the right-hand side become? 1/2. And then times 4 here. Right? Either 0 plus 1 is 2, squared is 4, times 2 is 8. Plus c. Okay. What is c then? 5/8, yeah, and negative as well. Okay, so then we can get an implicit solution. Just plug in this back in. -5. Okay, and that's sufficient enough for this problem.
If you choose the other side to be negative, would our solution still be the same, even though it's close?
It's fine, yeah. You can move this to be negative plus, that'd be perfectly fine. Yeah, it doesn't make a difference. Good. All right, so any questions so far? Okay, you guys can, you guys are good now, right? I think it's like, I don't know, it's not fair if like the same people keep asking. That's all I'm saying.
I did way too much of that.
It's good to participate, just, the professor should be, doing that. Okay, so this one I think can actually be solved for an explicit case, okay? Like, this is fine for the exam, right? You just move on, save yourself some time. How would you solve for y in this case?
You would multiply negative inverse and then subtract 1 and 1.
Right, so first thing you need is this on top, right? So you can take the reciprocal. This is gonna look hideous. Subtract the 1 over, and then natural log both sides. Oh, and also deal with the negative as well. Move the negative over. Yeah. So you could get it. It's not worth your time. Okay. Whew. Good. So, other questions? Yeah?
Number 4 would be,
That's what I listed too. Yeah. I thought the hardest ones, or maybe the newest ones, would be 4, 8, and 5. So 4 and 5 for sure. 8's not that bad, but it's a word problem. That's the only thing. Number 4. It's okay, don't worry about it. Number 4. Okay, so, okay, so part A, general solution. To y triple prime plus prime plus 36 y prime equals 0. So that's the easy one. And part B, does it say general or particular? I'll look it up. Sorry. So, some form of solution oh, it just says solve. If it just says solve, assume general solution. Kind of like the same way that like, what was the last one?
Yeah, the last one just.
Yeah, like the last one was just like solve this equation, find a general solution. A general solution to basically an inhomogeneous case. 108x squared or something.
Yep.
You have to. You have to solve this first and then use that for the second one. It has to be done that way. Yeah, even if like the problem just said general solution to this inhomogeneous one, you still have to solve the homogeneous case. Okay? You still have to do it. It's kind of just baiting you into not doing it, I think. Okay, so part A. Okay, so this is kind of half the times. So to solve these sorts of higher order equations, what do?
Characteristic and prime.
You assume y equals e to the rx, you get your auxiliary equation, right? So you know that y equals e to the rx. I call it the auxiliary, but it's really also called the characteristic equation. It's the same thing. I don't know, do you guys have the Stewart book by chance from calculus back in the day? I think they call it the auxiliary equation.
Yeah, and
That's the habit that I have. I learned from the Stewart book, so I always write both of them. So in this case, what's the auxiliary slash characteristic equation for this equation? 3 derivatives, so r cubed. And then, yeah.
12r squared.
12r squared, and then 36 r. So the main thing is like, there's no non-derivative parts. That's why they all have at least a power derivative. So how do we factor this? First, what do you want to pull out?
Pull out R.
R, for sure. R squared plus 12r plus 36. How does that factor down? It's actually a perfect square. So then, okay, so I guess on the side here, what are the roots? 0 and then -6 with the multiplicity 2. I've seen some of you guys write like, you just write it that many times, like -6, -6. Okay. Once you have this, what's the general solution? So what does the r equals 0 term contribute? Just a constant. You can think of it like C1 e to the 0x, e to the 0x is always 1. What does the -6 contribute? And then C3, x e to the -6x. So let's do the multiplicity. So that's part A. Part B. Okay, well we need this for it. This is our complementary piece. Right? The general solution to the homogeneous case, this is YC. So we just really need to solve for YP. It's 1 to 3, so I'd probably say let's not do variation parameters when you think about that. So use undetermined coefficients. So again, undetermined coefficients is usually easier to solve. Because all you do is like make a good guess, and then all you have to do is take derivatives, which hopefully aren't that bad, like the function is not that bad, and solve for coefficients, right? It's kind of brute force, but it's a lot of easy things. Variation parameters is kind of a few hard things. Okay, so this is the right-hand side. It's a quadratic technique. It's x squared. So for f, the right-hand side is just, let's just call it f. It doesn't really matter. What would our guess be? That's what you'd guess, right? ax squared plus bx plus c. So kind of following from that idea of like, if you kept differentiating this, or just like that rule that I gave you in the worksheet, right? If you have a polynomial of a certain degree, the guess should be the same sort of polynomial. Don't be deceived if there's no other terms, right? Like, you should still guess one with the lower order terms, bx plus c. That's all we're trying to point out here. So don't forget the bx plus c. To does anything here appear in the complementary or general solution?
Yes, the C's overlap.
This overlaps. Right? But this is a part of YC. So then what should we do to our guess? We shifted it by x. So mainly it's due to the, I guess you could say it's due to the r equals 0 part, the C1. We just shift everything by x. So we have ax cubed plus bx squared plus cx. Should we add a plus b? It actually won't do anything. If you add a plus d, it's just included here. So don't do it because you're just going to cause yourself more headache. Yeah. The idea behind this multiplication by the x to that degree, like here it's appearing once, so we multiply by just x to the first power. The idea behind that is like, then anything lower than that is probably already part of the complementary solution. So that's why we did. That's why we just don't need those other terms. This is our guess. What do we do to this yp now?
Oh, take the derivative.
We have to take its derivatives, and then what do we do with them? Plugging back into the equation. So, for instance, you're plugging it back in. To do that, you need the derivatives. Right? So, we need 3 derivatives. Great. It's okay. So that's yp. Derivatives. To plug in. Okay. So yp prime is what?
3ax squared plus 2x
X. Yep. Okay. Yp double prime. Let's keep going. 6ax plus 2b. And then yp triple prime is just 60. Okay, good. Yeah. Okay, so where's my equation? Here. Here's my equation. So we're going to plug this back into here. So that'll always work, right? Sometimes, I don't know. Like sometimes I kind of like this trick of like, you see the coefficients here, like 1, 12, and 36. What I like to do is like, instead here, I just add in the 36. Here, I add in the 12 to both sides, and then I just start tabulating the powers of x straight up, rather than plugging it all in and then doing that. Because you're going to take like 2 minutes to write down every derivative, right? So, anyways, let's get to it. So, triple prime, 6a, 12, y double prime, it's 12. 6ax plus 2b, and then 36 y prime, so 36 3ax squared plus 2bx plus c equals, right, the right hand side, 108 x squared. Okay. So when we're solving for the a, b, and c, even for like a general guess, not like a polynomial, the name of the game is just function type. Function type. Professor said it many times, and I'm basically beating it into. Right? That's how you organize the equations to solve for the constants. If you want to think about it algebraically, those are like your basis. Those are your basis vectors, your basis functions. So here, right, there should always be lower than x squared for a polynomial, so let's just start from the highest power, right? Right, equations. in the coefficients. So x squared, what do we get? What do we get on the left-hand side that has x squared stuff?
3ax times, or 3ax squared times 36, which is 8.
Yeah, I think this is this one, right? So, let's see. So, red, green, and blue. So, here's the blue. It only comes from this thing, and then don't forget the 36 in front, and the inhomogeneous part. So we get exactly 108, A equals 108, right, which is great. You already know that A equals 1. The sooner you can find constants, the better, because then when you find other equations, you can maybe just plug them in and get other constants then even simpler. That's x squared. Okay, next one is x. Okay, so x, I guess let's do that in red. So what terms have an x in that equation? 12 times 6. This one, so we have 12 times 6, which is 72. I guess I'll put in the A. Right, I'll put in the A. And then what about from that side? 72B. And then what about on the right side? 0. There's none. Okay. Yeah, I think the professor puts placeholders. I prefer to just write straight up equations. So that way you can make a matrix if you want to. Oh. You can make a matrix for A, B, and C if they turn out really bad. Okay, so plug in A. Plug this in to here. We get 70. Okay, let's just divide the 72s. B is negative A, which is negative 1. Right. Okay, and the last one is, I guess, constant or 1. Oh, I didn't. Right. So this one, x term. So naturally, everything left over is just the constant parts. 6a is 12 times 2b is 36 times c. So we have 6a plus 24b plus 36c. And then on the right hand side, 0. And then now what you have to do is take both of these and plug this in. Alright, so we get 6a is 6 minus 24b, or plus 24, but b is negative 1, so minus 24. It's like negative 18 plus 36c, 0. So what do we get for c? 1/2. And all we do is just plug this back in and then put it all together, right? So yp equals a was 1. That's the coefficient of x cubed. It's x cubed. B is negative 1. That's the coefficient of x squared. Minus x squared. C is 1/2. That's the coefficient of x. So plus x over 2. That's our yp. Are we done? No. What do you want to write for your general solution? yc plus yp. So then copy everything that you had. Right, remember that this is yc, the general form part A. So c1 plus c2 e to the negative 6x plus c3 is x e to the negative 6x plus x cubed over 3 minus x squared over, oh, no, x cubed, sorry, x cubed minus x squared plus x over 2. right? This is YC, and this is YP. Cool. Okay, yeah?
Going back, can you explain how you got the general form of the Y particles that they execute?
This one, right?
Yeah.
Okay, so first, if we just looked at this right-hand side without knowing what the complementary is, what would we guess? We would guess this quadratic. Right? Then go to the complementary solution, or this general solution for when it was 0, see if any of the pieces overlap. Right? It overlaps with this one once, right? So we have to scale it by x once.
So you can't just remove C, you can't just say ax squared plus bx, you have to multiply everything by x.
Yeah, we have to multiply everything by x. I mean, it raises this one to cubed, right?
And you want that to be cubed because you're going to take the third derivative. So.
That's in the end, like how it affects, right? This third derivative, it came into play for solving the constant, or the constant equation, which came into solving for C at the end of the day. Because prior to that we had A and B, but it involved that C. Yeah. So it involved all three.
And when you say like overlap, is it because C is a constant and there's also a constant in the Y general?
Yes,
Like,
that's exactly it.
when they overlap, is it always that kind of like a constant? Or will it also be a
No,
polynomial?
it can overlap like, yeah, with a polynomial or a trig function or an exponential.
So then why does C3x overlap with the CX?
Because this one came from the root r equals -6. It's mainly the exponents. It's mainly this exponent, and that's not related to this polynomial. This polynomial is from like e to the 0x, so to say. This is related for e to the 6x or -6x. So it's different. It's like a different function type. So because it's a different function type, and it's not part of, this isn't part of that. It's not related to this one. Are there other questions on this problem? Okay, yeah, you have it? Yeah.
How can you do the whole problem from
Yeah. Do you have one in mind, or?
I have one in mind.
Well, let's just see here all the numbers. Which one do you have?
2.5.8.
Like 8, and then. Oh, right, that's the last one, right? Okay, let's do number 8 really quickly, because that's on his exam, and I'd rather do that, I guess, to cover my tail. I'll just set it up, I think. I'll set it up. Because the word problem, that's basically half of the issue. So this is all the solving, so. Okay, so it's a word problem, so I may not copy the whole thing. But I'll list out basically the important parts. Okay. So wizard, I don't know, Harry Potter. So wizard creates gold. 1 ounce per hour. Continuously. Okay, his assistant steals, okay, or steals 5% of the current amount per hour. Or I guess ounces per hour. A. Model the gold amounts. WT with first order equation. You don't need to copy this. It's kind of just so, I don't know, for the video, I guess. And then B solve for W if W is 0 is mean. We probably won't do that part. We'll just do the modeling part. Okay. So basically, all the information should give us something about like the rate of creation and destruction of the gold, right? Basically, how much plus and how much minus. Right? You can kind of assume that like creating is plus and then stealing is minus, right? Especially because it's per time. That's when you know that these have to be quantities in W prime or dWdt. Only because of what the time is. Like it creates 1 ounce per hour, steals some amount per hour. So that's how you know that those are specifically for the derivative. Okay? So A. So dWdt. So if we create 1 ounce per hour, what should we probably do on the right side here? Suppose you like forget about the guy stealing, right? Forget about him stealing. Suppose you just create gold at 1 ounce per hour. What's your rate of change of gold then? 1 ounce per hour, right? It's 1. You don't have to include the units. I'll just like write in parentheses. Right. But it's just 1. Right, that's the created part. So now, let's look at the guy stealing it, right? He steals 5% of the current amount. So what would the current amount of gold be? It would just be times W. dWdt is the rate of change. The flat out amount is W, right? 5% good is 0.05. If you want fractions, that's 1 over 20. Doesn't matter. So minus, because he's stealing, 0.05, or you can write 1 over 20. And then W for the current amount. And that's all your equation is. So if you want to write this maybe a little differently, I guess this is, okay, right, label it. This is stolen. Okay, so what does this mean? It means dWdt is 1 minus, I kind of like writing this as a fraction, but it really doesn't matter. Right? That's your equation to solve. Okay. And then, right, initial condition is W0 is 1. Okay. That, I think, is, you can do that in like 2 different ways. You can use an integration factor if you want to. You can separate it if you want to. Both are fine. Right. When you separate it, though, you have to divide by this whole term. This is kind of like AW plus B or something like that. So when you separate it, you have to be a little careful with how you integrate 1 over this thing. But it's doable separation, doable with integration factor, whatever you want. Is that okay? Is that enough? Cool. And you should solve that in the solutions, so that'll be good. All right, so 1 and 2.5. So you said number 8?
Yeah, 2.5. It was
Last question. 2.5 number 4? Or number 4 the... So 4 and 8. Let me take a look at them.
I have it.
Oh, okay. I'll pull it up.
So 2.5.4 is to solve the initial value problem. Y double prime plus 9y equals cosine 3x plus sine 3x. So the initial conditions y of 0 equals 2 and y prime of 0 equals 1. And then 8 is find the particular solution y double prime minus 2y prime plus 1 equals sine x squared. It's okay to be answered.
Right, okay. So, are those both on the homework then?
Yes.
Oh, yeah.
Okay. Out of those 2, I think I prefer 4. Number 8, because this has definite integral, you kind of know that it's probably a variation of parameters. Like, how do you know what to do it though for number 8? Let me just write down the problem. So, just write down somewhere. So, I think I'll talk about how to set up each problem. I think that's good. Oh, it is X.
I guess it doesn't matter. Well, we could.
Yeah, it doesn't matter. Yeah. Okay, so when you look at this problem, right? Do we know how to guess something for this?
It'll go on.
I don't think it'll go on forever, but it's gonna get like, we're probably gonna get like, oh no, wait. Yeah, it will go on forever because you get powers of X. Yeah. Yeah, so it'll go on forever. Also, yeah, I don't even know what you would guess. Like, I don't think you'd want to guess that. So in the worksheet, right, I gave basically the three general forms: polynomial, exponent, and trig function. Basically, those are the ones you're looking for. This isn't one of them, so you probably look for variation parameters. Why is this definite integral okay? It's because this is not integral. We should just do it. Should we just do it? Raise your hand if you want to see it. That's convincing enough, yeah. Okay, and I'll do it 4 after that. This thing is 4 is just a lot, but it's kind of like this, a lot of fun. But we'll talk. Okay, so first, we need YC. So to get YC, we have to solve when it's 0. So we have to look at the auxiliary equation. What is it in this case? Plus 1 equals 0. So r minus 1 squared equals 0. R equals 1 with multiplicity 2. Okay. We have that. We know that. Okay, so right. It's like I can write it. Like due to this tells us to use variation of parameters. So if our R is 1 with multiplicity 2, what's our complementary solution look like? Cool. Okay, so now, second thing for variation of parameters, we have to set up that system of equations, right? Or the Wronskian thing. Right. I'm sorry, I definitely prefer this. The system. So
and I prefer it that way too.
The system that we'll have is U1 prime, Y. I jumped the gun a little bit. Let's see how the complementary solution. You want to identify Y1 and Y2. Right? So once you have this, it doesn't matter, but just set one to be one of them, Y2 to be the other.
Maybe the X and X.
Yeah, and it doesn't matter which order. Sorry about that. So I set that up first. Once you have that, then we're ready to set up the system. So first equation. Okay, so let me ask you guys, what should the first equation read as? U1 prime, Y1, so that's e to the x, plus
U2 prime.
U2 prime, Y2, so x to x, and that equals 0. Second equation, U1 prime times, because that's Y1 prime, right? It's its own group. And then U2 prime, we have to differentiate this into product. Yeah, that's a nice way to factor. Yeah. Anyways, right, derivative it or differentiate it to a df. F of x was sine of x squared on the right. Do you have to divide anything? No. Okay. The coefficient was 1. That's why I made the check. The coefficient was 1, so we didn't have to do anything. in this case. Right? Most of the problems are posed that way. That sometimes they want to, if they're looking to get you, there's something else up here. Right? So maybe just to be like super divided by 1, right? Just to be super
That's a good way.
methodical. Like we see that this is really affecting the Cauchy equation because that's an x squared out in front. If that's forgotten, that thing is junk, whatever you get at the end. Okay, so this is what we get, and then we have to solve for u1 and u2 prime. Okay, so we want to use one of the equations, probably the first one, to eliminate something in the second one, right? So what can we do here? Take -1 on the first one, add the second, or take root 2 minus root 1, right? So 2, or second minus first. What's left? That goes away. What's left multiplied to the u2 prime? Even at x, so I should take out that bracket. And equals sine of x squared. Okay. Second minus first, so that thing is still positive. That's x prime. Isolate the u2 prime. And it's just e to the negative x, because they're dividing, and a sine of x squared. Cool. Not bad, not bad. So we go back and solve for u1 prime. Okay. So easiest, it's usually easiest to plug it back into the first one. The second one became differentiated. It's going to usually have more things. Let's go back to equation 1. Plug it into the first. What do we get? So u1 prime e to the x is still there. Now we have u2 prime x e to the x. So what cancels? Exponents, right? Plus x and then minus x. That should go away. And we'll be left with an x and a sine x squared. This equals 0. That's the 0 on the right side. And then isolate for u1 prime. Again, well, this will become negative. And then the same thing, negative exponent here. I already forgot the negative side. Negative x e to the negative x sine of quantity x squared. Okay, so now what do I have to do to both of these guys? Integrate. Can we integrate any of these? No. This is where we leave it as definite. Right? So can't anti-derive. So all we do is just have definite integrals. So u1, all we need to do is just say it equals, yeah, I guess there's a negative there. Just set arbitrary bounds. Doesn't really matter. 0 to x is probably the easiest steps. The only thing is you have to change these to dummy variables. So, yeah, you can write x hat, you can write t, you can write whatever the heck you want. So x hat is the negative x hat.
Negative sailboat. Negative sailboat.
X hat squared.
Sine of sailboat squared.
So x hat. A lot of times people also like, usually people use t, right? But anyways, let's impose definite bounds. I pull out the negative out in front, just in front of everything. It doesn't really matter. But this is all you need to do. Okay? This, in principle, right, by like fundamental theorem of calculus, this is whatever its antiderivative is. Lower bound is just say plus some specific constant that whoever knows. Right? Same thing for u2. Probably just use the same bounds. 0 to x, e to the negative x hat, sine of x hat squared, dx hat. Right. So these are u1, and U2. And then I kind of like to rewrite that, but I think it's best to stay on here. Okay, so once you wanted U2, then you know that YP is given by what? U1, Y1, I guess let's copy it down to the X plus U2, Y2, which is X to the X, right? So all we need to do is recopy all of these integrals with like an e to the X and X e to the X in front here. Okay? Then probably the last thing you need is that Y is YC plus YP. Right? You can do this. Right? Okay. Any questions on that one? Okay. The one you're asking is kind of, it's just very computational because it's a lot of derivatives. But it's a good one because it's something where there's a repeat. Okay, so 2.5.4, right? This one. And it was y double prime plus 9y equals cosine 3x plus sine 3x. Any coefficients there? Oh, and there's initial conditions. I really. Okay, that's okay. This is good practice. Let me write it down. So, just a warning, right? When we have an inhomogeneous equation with initial conditions, solving for the constants is a little bit. It's not bad. It's just you don't want to forget things. Right? And your solution at the end of the day is this. The initial condition determines coefficients here, but it also has to be plugged in here. So that's the warning. The YP can affect the outcome. Okay, so first thing is to usually do solve for the homogeneous or complementary solution. Get YC. What's the auxiliary equation here? R squared plus 9 equals 0. What are our roots?
Plus or minus 3i.
Plus or minus 3i. What's our complementary solution?
C1 cosine 3x.
C2 sine. Cool. All right. So now, if we look at the right side, this is our inhomogeneous part. Okay, so there's two things you can do: is variation of parameters or undetermined coefficients. I'd always say try for variation. Or sorry, try for undetermined coefficients, because that's always easier to solve, I think, in general. If you're out of luck, then, or he says use variation parameters, then do that. Like, for example, this one. You don't know how to deal with that. Use variation parameters. Something like this, or like the other time it was just like a polynomial. Use undetermined coefficients. So here, we use undetermined coefficients. What should we guess for YP before we even know that these are the roots? A cosine and B sine of 3x. Yeah, but we see that these are the complementary solutions exactly, right? So how would we have to rescale this? By x. Right? In other words, ax. Oh, I wrote cosine twice. Oh, sorry. Yeah, sine. Oh, whatever. Yeah, cosine x. So, yeah, it's just lots of reds. Yeah?
What we should multiply by x squared?
By x squared. If the root is repeated twice. So right, this is the main thing that I wanted you to get to, is that this is your yp here, right? What you do is then take derivative, take second derivative, plug it in, solve for a and b. Right? A lot of derivatives. Right? And then you have to solve for the constants for yc too. So I kind of want to just get to the guess here. I have an example that has one where you guess squared, if that's okay. You want to try? If the inhomogeneous part is part of the complementary, and that complementary has repeated roots, then it would be squared, or maybe even higher. Right? So like, kind of referring to the worksheet. If you have it in front of you, or online, on the back side with the exercises, okay, so, do you want to continue with this one? Yeah? Okay. So, this is yp. Okay, so if you want to see one with multiplicity 2, look at the second exercise. Y double prime minus 2y prime plus y equals e to the x plus x cubed. Maybe you can drop the x cubed. Right? That's one where it's multiplicity 2. It'll have e to the x with multiplicity 2. For that one, we'd have to guess x squared e to the x. So maybe we'll do that after. We're going to do this one. We're going to need a longer space. Okay, so that's yp. So we need a derivative and second derivative. Actually, we just need a second derivative, but that means we need. But okay, we still need to do a lot of this.
So much fun.
So this is why I was hesitant to multiply the x over, because if it's just like this, it's already set up like a product group, rather than working with this, right? So I would maybe even just look at this form instead of this, because this is already set up for a product rule for you. Right? So like yp prime is just a cosine 3x to be sine 3x plus x times derivative of this, right, negative 3a sine 3x plus 3b cos 3x. Differentiate this again. Okay, right. So this is going to be negative 3a sine 3x plus 3b cos 3x plus, this will give us two new terms. Differentiate the x, negative 3a cos 3x. I'm sorry, black marker. And then plus x times derivative of this, negative 9a cos 3x plus minus 9b sine 3x. Right. this should be simplified a little, I think. Right? That and that looks like it can add together. I think. They're adding, right? Yeah, so you can have negative 6a sine 3x plus 6b cos 3x plus x times negative 9a cos 3x sine 3x. Okay, good. So, there's a trick here. There's something to observe here. So, the equation is going to be, well, we're putting yp into here. So you have yp double prime plus 9yp, right? Yp's here, right? If we multiply this by 9, you get 9a and 9b. It kills it, right? It always does this. The one with the x is supposed to nullify out. That's how you tell that your derivatives are correct, actually. So like, it's not just like by chance. It has to happen, otherwise you know that you made a mistake back there. So that's what's supposed to happen. And the same goes for higher multiplicity roots. Like if we do that example that I was talking about, like the one in the worksheet, you'll notice that like x squared e to the x and x e to the x cancel, and you're left with whatever the coefficients e to the x are. It'll always work out that way. So here, plug it in, right? So yp double prime plus 9yp, this is that, minus 6a. I'm just gonna drop the 3x. 6a sine plus 6b cosine, right? Plus x negative 9a cosine minus 9b sine. Inside all these brackets is a 3x.
But the 3x is
Right? And then plus 9 times yp, which is this, right? A cosine 3x plus b sine of 3x. Okay? Then you can go back and just fill in all the 3x's. 3x, 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 3x. Okay. And notice that this cancels perfectly. And all this has to equal, cosine plus sine. Right? So again, what are our two function types in this problem? Sine, cosine, and technically the x sine and x cosine, but we see that those already cancel out. Right? So the coefficients here, cosine x, cosine 3x. What do we have? What do we have on the left side? 6a or 6b? We have the 6b, right? So this one, we have this on the right and this on the left. So we have to have 6b equal to what? 1. Sine of 3x. What's that one's coefficient? Well, that's coming in here. Oh my god. Flipping green. Yeah, so you get negative 6a has to equal positive 1. So then what you get is b is 1/6 and a is negative 1/6. And then yp then is x over 6 times a is -1, that goes up in cosine. So negative cosine 3x plus sine. So that's your yp at the end of the day. Question? Yeah.
Why do we add the x when we're guessing yp?
Right. So we added the x because, well, if we didn't, right? If we didn't, this is just the same thing as the complementary.
Oh.
Exactly, actually, in this case. That root only has multiplicity 1, so we only need to scale it by x in the first term. Now, if it was a higher multiplicity, it would be like x squared. But it's only 1 in this case. Yeah?
So when we're doing the definitions, that's referring to the general solution, right? We're going to add both the particular and the complementary.
Yeah. We're not near done. Actually, we're not done. Because this problem has initial conditions. Right. We're not done. You're free to leave now, for sure. Yeah, this problem's not done. So, at least it's on videos. Sorry, what you have to do next is still get the general solution, right? Which is yc plus yp. But in this case, it's going to be c1 cosine 3x plus c2 sine 3x plus x over 6 times this thing.
Also, you have to do it.
Yeah. This is why we also need this derivative.
You got this.
That's not the
I mean, I don't know.
Oh yeah, but like
Probably not this.
not this long.
One, 6, so that's our derivative. That's our general solution. Y of 0 is 2. So we plug in 0. What do we get to this one? Right, we get C1. This should go to 0. That's 0. Right, so C1 is 2. Great. Not bad. Okay, Y prime of 0 is 1. So we have 1 equals, okay, what's left here? 3C2 minus 1 here, so minus 1/6. And this one goes away now, because that has an x in front. So we get 3C2 is 7/6, C2 is 7 over 18. Cool. Plug that back in and we copy everything and you're done. I mean, main ideas here though, right? Well, so forget the algebra, right? What you're after is the concept, the train of thought. That's the way you're after, right? You start out with the complementary solution and then you try to do an undetermined coefficient for the right side. You see it repeats it, so you have to account for it accordingly with scaling by x, right? That's what you want to take away. Then you solve for the coefficients by finding derivatives and plug it into the original to solve for the coefficients. That's apparently the worst thing in the world. All this. But once you have the coefficients for yp, right, we get the general solution, and if we have an initial condition, then we have to work with that general solution. with the YP included. But you see, it can change things, right? So that's what you want to take away from this, not the algebra. You have to make sure you're sharp on that though for the exam, but right, the train of thought is what you want to always have down. All right, so that's all. I'm kind of half willing to do that one in my exercises with the multiplicity of 2. Who's interested in that? If we have to go, then let's not. Right? Because the derivatives get kind of nasty too, so it's okay. If you guys don't feel like it, then it's fine. Yeah, I'm fine. Okay. It's on video, so everyone who's leaving, it's perfectly going to be online, so it'll be good. All right. So I want to do this just because it's multiplicity 2, one that's higher. It should only take like another 10 minutes. Okay. So my worksheet. And I'm going to simplify it because I don't want to deal with more than I want to. Okay. So let's just simplify it to y1 prime minus 2y prime plus y equals e to the x. Let's drop that x cubed piece. If you have the x cubed piece, you just guess ax cubed plus bx squared plus cx plus d. That's 4 constants to solve for. Let's not do that. Okay? Let's look at this. 1, auxiliary equation, get the complementary solution, right? What's the auxiliary equation here? R squared minus 2r plus 1. How does that factor? R minus 1 squared. We have 1 with multiplicity 2 as a root. Okay. Once you have that, you can construct YC. So what is that going to give us? C1 times e to the x, and then C2 times x e to the x, right? Now, we need to guess a particular piece. Something cool with this problem is it's doable both ways, variation parameters or undetermined coefficients, and it's not too bad either way, I think. Right? But if you do it undetermined coefficients, you have to watch out for this multiplicity, right? So if we do undetermined coefficients, we need a YP for this e to the x. So before you know the multiplicity, what would you guess?
Well,
Yeah, a to the x, right? So it's like you always think about what you guess beforehand, and then look at the multiplicity 2. So how should we scale this? X times x squared, right? And that's all it is to this guessing thing. Right? Just see if it's appearing there, how many times. Bam, that's how many times you multiply by x. So with this, just to rush through the computations, right? Yp prime is going to be a times 2x e to the x plus x squared e to the x. Yp double prime is going to be plot the a again, so we have 2 e to the x plus. There'll actually be double of these because of this one. Okay. And that's what you get. Right? And then overall here, there's really 4x. Okay. Same thing as before, right? Solve for coefficient, or there's only one, there's a, right? By function type. Right? Plugging it back into there, right? So here's kind of where maybe because we're doing this informally, right? What I sometimes like to do is take these and just rescale it already. So like this is Yp. If you want negative 2 Yp prime, well, negative 2 on the front, and this is Yp double prime, right? So now we just consider yp double prime plus over minus. Right. Basically, I'm just kind of like manually inserting this as we go, kind of on the fly. So for this, how many function types do we see? We don't have x squared e to the x. What else do we have? Right, x squared e to the x, x e to the x, and then what else? Just e to the x. Right. Okay, so what terms have x squared e to the x? Right. So yp has a, right? Y minus 2yp prime has minus 2a. Yp double prime has plus a, right? On the right side, we have none of them. But this already adds to 0 anyways. This is the sign that you differentiated, right? Go to the next one. This one has nothing. We have minus 2yp prime, that's minus 4a. Part of that x e to the x's. And then yp double prime has another 4a here, but that's positive. Do we have any on the right side? No, there's another sign that we differentiated right. E to the x now, right, yp has nothing, that's the squared one. Yp prime also has nothing. We only have this one, right, 2a. And then what was on the right side? One of them, right? That's from this guy. 2a equals 1, a is 1/2, yp is 1/2 x squared e to the x. Okay. And then you can do whatever the heck you want from there. This is an example with order 2, right? Hopefully that's getting more comfortable with if you have to deal with multiplicities. Okay. Okay, so that's it. That's it. This extra like 7 minutes. So keep it efficient. Do you have any questions about something that was during the video or during the video during the review? Just please come and ask, and I'm gonna shut this off.
Never mind. Yeah, you have to.